Today we are going to discuss pure rotational spectra under atomic and molecular physics. So let us get started. So when do we see rotational spectra? So let me change the color to which is purple. So rotational spectra will be seen in what we call heteronuclear molecules with a dipole moment. So heteronuclear molecules will have dipole moment like water. And when do we observe spectra? Because the dipole moment will interact with the electromagnetic radiation. So the dipole moment will because of the electric field, the dipole moment will experience a torque, and that is when we have rotational spectra. So in this case, in today's lecture we will be discussing only pure rotational spectra. There will be no vibrational spectra. That we will do in the next lecture. So the energy due to rotational spectra E, this is rotational energy due to rotation. So that can be written as L square by twice I. Like we have for kinetic energy we have P square by twice M. Here we have L square by twice I. L is the angular momentum. And we know the values the angular momentum can take. Angular momentum can take the values J into J plus 1 H bar square divided by twice I. So these are the so the angular momentum can take, so L square can take this value. And we are dealing with a molecule such that the moment of inertia along principal axis 1 and 2 are the same, and it is equal to I, and the moment of inertia along the third axis is 0. So this is what we call the rigid rotator, and I here is equal to what we call mu r square. Mu is the effective mass and r is the distance between the molecules. So this is a molecule that is rotating about its center of mass, and if you calculate the moment of inertia, it comes out to be mu r square. Mu is the effective mass and r is the distance between the two molecules. So we can write the energy in terms of inverse of wavelength, and this energy is E by hc. And that you can write it in the form of some constant which is B, J into J plus 1. So J is the quantum number in this case. You can take the value 0, 1, 2 like that. And B here has the value H divided by 8 pi square I into C. C is the velocity of light and I is the moment of inertia. In fact, we can also define something called angular frequency of rotation. So if we know the energy, then the angular frequency square, omega square, is equal to twice E by I, and that is equal to, you can easily see it is actually H bar square J into J plus 1 divided by I square. So if we know J, then we can find out the angular frequency of rotation. So the difference in the inverse of wavelength between two consecutive energies is given by this. F at J plus 1 minus F at J is actually equal to 2 times B multiplied by J plus 1. This you can easily check from the expression. B is the constant which we have already defined before, and the selection rule for transition is delta of J is equal to plus minus 1. This is for rigid rotator. Remember, this condition has to be satisfied. Now, if you consider centrifugal force, then there will be a kind of vibration. So there will be a vibration energy also, which is linked to the rotation. So this is the term that denotes the energy due to vibration. So this is the term which we had already discussed, and this is the new term, and that is equal to minus dj square g plus 1 whole square, where d is much less than b. So you can basically neglect it unless and until j is very high. D is very much less than b. And now we had talked about rigid rotator. Now if instead of rigid rotator we have like something like a symmetrical top, where the moment of inertia along axis 1 and 2 are same, equal to I, and the moment of inertia along the third axis is not 0, but it has some finite value. In that case, the energy, or the inverse of the energy divided by hc, or the inverse of wavelength, can be, it will be defined by two quantum numbers, j and lambda. And in that case, like we had fj is equal to bj into j plus 1. So this one will be modified, and we will get bj into j plus 1 is there, then plus a minus b lambda square. B we know, a is a similar quantity, but it is related to moment of inertia of the third axis, about the third axis. So this is h by 8 pi square I3c, and j here is limited by the values of lambda. So j can be only greater than or equal to lambda. So j can take the values lambda, lambda plus 1, etc. So below lambda you don't have any value of j. So those are the missing energies when we have rotating molecule like this one, satisfying this condition. So in that case, when lambda is not equal to 0, our selection rule is delta j is equal to 0 plus minus 1. So we can now do a problem. The moment of inertia of a rigid diatomic molecule A is 6 times that of a diatomic molecule B. The rotation energies of the two molecules are equal. Then show that the values of Ja and Jb are this. So you have 4 options. So rotation energy is proportional to what? So you have two molecules. So you will have B, A times Ja. This is the rotation energy is proportional to this Ja plus 1. Okay. This is for molecule A, and for molecule B it will be B. The B constant is already defined before. So B, B, and then we have J. We have J for the molecule B, and JB plus 1. Okay, so we are just going here in this like this. We are using this proportional to this. So the rotation energies are same. So now, so we know that B is proportional to 1 by moment of inertia, and from here you can find out. So here it is given the moment of inertia of A divided by moment of inertia of B is 6. So from there you can calculate. So so according to here, so B A by B B okay is equal to 1 by 6. Okay, here. So from there you can calculate what were the values of J and JB, and you can check. I think this will be the correct answer. Okay, we go to the next problem. So consider the hydrogen deuterium molecule HD. The mean distance between the two atoms is so much nanometer, and the mass of hydrogen the mass of hydrogen atom is 938 MeV by C square. Then show that the energy difference delta E between the two lowest energy levels is 9.2 into 10 to the power minus 3 electron volt. So the expression for energy is some E, some constant into J plus 1, where the constant is H by 8 pi square into I. So energy difference between two consecutive energy levels, energy difference will be 2A into J plus 1. And for when we are considering two lowest levels, the energy difference will be only 2A. Okay, so what we have to find out, what is the value of 2A? That is what we have to find out. And this is nothing much. So we know that so this is the term moment of inertia is there. These are, so moment of inertia is mu r square. So I is equal to mu r square. I is equal to mu r square. Mu we have to find out, r is given in the problem. R is given in the mu r square. So mu is what? You can easily check. So deuterium atom has 2 protons, so its mass will be twice that of the atom of hydrogen. So if you do, you see mu is equal to 2/3 mH. Okay, and so R is given. H. So what? So we have to find the answer in electron volt. So best is convert H into, H is given, generally we know the value of H in joule second. So you have to convert that into electron volt second. So this is straightforward. If you do it, it will be like this. H is equal to 6.3 into 10 to the minus 16 electron volt second. And now if you put the values in this expression, you are going to get the answer. So answer is twice A. So you will get the answer. Next we have the absorption lines arising from pure rotational effects of HCl are observed at 83.03 centimeter inverse, 103.73, 124.30, 145.03 and 165.51. Then showed that the moment of inertia of the molecule is 2.8 in 10 to the minus 47. So we know that the difference in the inverse of the wavelength between the level J and J plus 1 is twice B J plus 1. Okay. Similarly, then the difference between two consecutive, so difference between two, so this is one line. So this represents a line. Okay, this represents a line. So when J is equal to 0, it represents a line. When J is equal to 1, it represents a line. When j is equal to 2, it represents a line. J is equal to 3, it represents a line. And the distance between the two lines so distance between two consecutive lines in centimeter inverse will be distance between two consecutive lines in units of length inverse will be this. So delta f j plus 2 j plus 1 minus delta f j plus 1 j, and that you can easily check, comes out to be 2b. Okay, so 2b is equal to, so from here 2b is equal to 103.73 minus 83.03, that is 20.70, or 2b can be written as 124.3 minus 103.73, 20.57. obviously there is a unit, so like that you can calculate, you can keep calculating, and you can see there is a slight variation of 2b. So here it is 20.7, here is 20.57. So what we have to show is the moment of inertia of the molecule. So from here you can get an average 2b. Okay, once you have an average 2b, once you get b, you can find out the moment of inertia of the molecule, because b contains the expression for moment of inertia that we have seen, like this. So once we find b, we can find out what is the moment of inertia of the molecule from this expression. So we are all using the expression for rigid rotator. Similarly, the separation between, another problem, the separation between neighboring absorption lines in a pure rotational spectrum of HBr molecule is 2.23 electron volt. The molecule is considered a rigid rotator, and the atomic mass of bromine is 80. Show that the corresponding line separation in DBr, deuterium bromide, is 1.128 electron volts. Now the separation in electron volts, or separation in energy, is proportional to 2b or b, whatever you say. So separation in the case of hydrogen bromide divided by separation in the case of deuterium bromide is equal to your value of b in the case of hydrogen bromide into divided by value of b in the case of deuterium bromide. And we know the relation between b and moment of inertia, and moment of inertia is mu r square. So if the distance remains same, then we can write this expression in terms of effective. So we can write it in terms of effective mass, mu d by, or reduced mass rather, mu d by mu h. So mu d by mu h we can find out from whatever is given, whatever data is given, and from there we can find out what is St. It should come out to be 1.128 electron volt. So we'll go to the last problem. So in HCl, hydrogen chloride, the transition from J is equal to 0 to 1 occurs at 20.68 centimeter inverse. The molecule is considered to be a rigid rotator. Show that the wavelength of J is equal to 14 to 15 transition is 32 micrometer. So J is equal to 0 to 1 transition occurs at 20.6 centimeter inverse. Immediately tells me the value of 2b is 20.68, unit is centimeter inverse. Okay, unit is centimeter inverse. And the difference in the inverse of wavelength is is twice b j plus 1. So now in this case j is equal to, in this case j is equal to 14, right? So j is equal to 14. So so once we know this, so j is equal to 14, b, the value of twice b we know, so from there we can calculate the value of inverse of the wavelength that is absorbed, and from there inverse of the wavelength we can calculate lambda. Okay, so lambda we can calculate. Once we know this, just by inverting it we can calculate lambda. So you have to find out lambda, and it should come out to be 32 micrometer. So we are going to end here, and next lecture will be about rotational spectra, and at the same time we will consider vibrational spectra also. Thank you.